Okay, so to take up where we left off in the end of the last class, this is basically what we've been studying so far. First and foremost, we've been studying what we call the pH scale, okay? And as you know from your junior cert, what the pH scale is, it's a scale that measures the strength of an acid or a base. So therefore, it's a scale that measures the strength of an acid or a base going from 0 to 14. Now, I did say to you before that it does extend beyond 14, it does extend below 0. There are acids that have pHs of greater than 14 and less than 0. But because usually the dilutions that we use in the lab are of such, say, 1 molar, 2 molar, 0.1 molar, 0.5 molar, usually the pHs that we use in the lab lie between 0 and 14. But that's not to say that pHs can't exist outside those. They can, okay? That's the first thing. The second thing we learned was that the strength of an acid or a base is directly associated to its power to dissociate. Okay, so if you take the old Arrhenius theory that said that an acid is anything that produces H plus ions in solution, what he was hinting at there was that acids, when they're placed into water, they break up, they dissociate. Now, the level of dissociation is the power of the acid, okay, or the pH. And we already know that if you take the pH as being the formula minus the log of the hydrogen ion concentration, well then all we have to do to make the connection between the hydrogen ion concentration and the pH is that formula there. So if I take, for example, 10 to the minus 1 and I bring it up here and stick it into the formula, minus the log of 10 to the minus 1, my answer will come out as 1. So that'll give me a pH of 1. And likewise, 10 to the minus 3 will give me 3, 10 to the minus 6 will give me 6, 10 to the minus 12 will give me 12, and so on. Neutral, as we know already, is 7. Okay, 7, which is in the middle of this pH scale, represents substances that have the same concentration of H plus and OH minus. If we go either side of 7, what we notice is that the H plus concentration is higher than the OH concentration, okay? And if we go above 7, well then we've got a concentration of H plus, which is less than OH minus. So just keep that in mind, that on either side of 7, we're dealing with hydrogen ion concentration here on this side being greater than OH minus ion concentration. But on the base side, you've got a hydrogen ion concentration which is less than the OH minus ion concentration. And don't forget that we told you when you multiply the concentration of H plus by OH minus, you must always get 10 to the minus 14, which is Kw, the ionic product of water. Okay. Now, again, just to finish this off, make sure we've got everything covered. As we go above 7, we're in the basic region, which means, as I said already, that your OH concentration is high. And if you go to the acidic side, well, then you've got your hydrogen ion concentration being high. Okay, and that's what it says here in terms of increasing hydrogen ion concentration, and down here increasing hydroxide ion concentration also. So if you're producing more H plus and less OH minus, you're on the acid side. If you're producing more OH minus and less H plus, you're on the basic side. And they're all linked together by that formula up there. pH is minus the log of the hydrogen ion concentration. Now we're going to come back and practice that again today. We're going to take a look at it maybe from just a deeper vantage point in terms of trying to figure out first of all what the concentration of the acid is before we fill the hydrogen ion concentration into the pH formula. Okay, so it's clear to see that the higher the concentration of H plus, the lower the pH. All right, now that seems a little bit counterintuitive, but if you think about it, if you have two hydrogen ion concentrations, let's take a hydrogen ion concentration in moles per litre of 10 to the minus 3 and another one of 10 to the minus 6. Which one of those is larger? Now, obviously, because the index, because the power is negative, then obviously the closer the power is to 0, the bigger the number. All right. So this one would obviously be a higher hydrogen ion concentration than this one, which basically means that this one has a higher pH and this one has a lower pH. And if I work out what minus log of the hydrogen ion concentration is, the pH here is 3 and the pH there is 6. So just keep in mind that when your powers are negative, the bigger powers are the ones that are closest to 0. Some people do still get that confused, but just keep that in mind. Likewise, the lower the concentration of H plus, the higher the concentration of, the higher the pH. So if you have high concentration of H plus, you get a lower pH towards 1. If you have a lower H plus concentration, you get a higher pH towards 7. When the hydrogen ion concentration is the same as the hydroxyl ion concentration, then the pH is 7. And the reason for that, as we already know, is because 10 to the minus 7 multiplied by 10 to the minus 7, that's when they have an equal concentration of both H plus and OH minus. When you multiply those together, you follow the rule of indices. You keep the base and you add the powers, which is minus 14, meaning that that's the ionic product of water. Remember that? That's Kw. So what we are describing here when they're equal is water, which means that if you take one of these and fill them into the pH equals minus the log of the hydrogen ion concentration, you're going to get 7. That's your pH. Okay. Now, just on the scale of things, you can be asked this. These are normal everyday substances that have varying pH values, all right? The household substance or the natural product with probably perhaps the lowest natural pH out there are lemons. Lemons are extremely bitter. And again, the more bitter a substance or more sour a substance, the more H plus is present. If you go right back to the start of this chapter, we spoke about acids having a sour taste. Obviously, the stronger the sour taste, the greater the dissociation, the lower the pH. Okay. Then we move to wine. Now, wine has a pH of 4, but wine is an alcohol. Wine is CH3COOH. It's ethanoic acid. Okay. When the alcohol is turned into that acid, so you've got your C2H5OH, that happens to be your alcohol. When you put it into oxygen, it turns into CH3COOH. And in fact, the longer you leave your wine open, the more acidic it becomes. Hence the reason some people say, oh, the wine has gone sour. Of course it has, because the alcohol, C2H5OH, has been exposed to atmospheric oxygen, has been oxidized to the corresponding carboxylic acid, which will drop the pH significantly from the normal pH of about 4. Rainwater, 5.5, naturally. Now, this isn't acid rain. Acid rain has a pH of about 3 or 2, okay? This is the natural rainwater, because when you let water down through carbon dioxide, which is naturally in the air, when these two combine, they form H2CO3, which is carbonic acid, which has a pH of about 5.5, okay? Human blood, very, very slightly above neutral, roughly about 7.5, so it's slightly basic. Baking soda, 8.5, detergent, 10, and bleach is 12. And again, as I said to you before, you'll find, including baking soda, they're all cleansing agents. People use baking soda to clean things, as well as using it to cook with as well, all right? So when the pH goes above 7, particularly into the regions of maybe 9, 10, 11, you're dealing with detergents that are very, very good at allowing the hydrophobic fat molecules, water hating fat molecules, to be linked to the water in order to be pulled away, and the item that contains that fat then to be cleaned. So pH is measured by universal indicator. Now, what's a universal indicator? I think the name is a little bit misleading. It is not a single indicator. In fact, universal indicator, as we already know, has a range of colours that it can turn into. If you remember in junior cert, you had your red cabbage experiment where you extracted red cabbage juice and then you tested all various different substances and you got different colours, okay? The reason why universal indicator can give so many colours is because universal indicator is a mix of indicators. It's not just one indicator. It's a load of indicators added in together that at certain pHs reveal their colour, okay? So keep that in mind. And what it does is it changes its colour depending on what pH the substance has. Now, normally, when we're using universal indicator, we've got a strip of paper with all the colours on it that we can match up to. We add the universal indicator into the substance, we hold it up to the paper, and we simply read off the pH. It's a fairly easy thing to use. Or nowadays, if you haven't got universal indicator or universal indicator paper, you may use a pH meter, which is nothing more than a probe that you stick into the liquid and you read the pH from the top, okay? So it makes life a little bit easier for us. But just keep in mind, if they ever ask you, name 2 ways to measure the pH. 1 is using universal indicator. 2 is by using a pH meter. What is a pH meter? It's nothing more than a glorified calculator that can work out minus the log of the hydrogen ion concentration it finds when it's placed into the solution. So all it does is minus the log of the hydrogen ion concentration. It can only do one calculation and hence turn your concentration of hydrogen ions into pH. Now, dissociation constant Ka. Where did we see K before? We saw K before in two places, Kc, Kw. And if you remember back, they came from the result of looking at a system that was in equilibrium. First of all, if we had, let's just take A raised to the power of A plus B raised to the power of B in dynamic equilibrium with C to the power of C. What did that give me? That gave me Kc, which is the equilibrium constant expression for this reaction at a given temperature. And it was, if you remember, C raised to the power of C over A raised to the power of A times B raised to the power of B. That was Kc. Okay. Then we came across Kw. Now, where does that come from? That comes from water. Water sets up a dynamic equilibrium with its own ions. Now, how do I know that water slightly dissociates? Because pure distilled water, deionized water, still conducts a tiny current, meaning that there's a natural amount, a very, very low amount, but a natural amount of dissociation that takes place. So there is, in a glass of water, there is a dynamic equilibrium occurring between the water molecules and their ions after dissociation. And we found out that Kw, therefore, was H plus times the concentration of OH minus over the concentration of H2O, which, as we said at the time, because water dissociates to produce the same number of H plus and OH minus, we could write that in shorthand as H plus multiplied by itself over H2O. Okay, that's where we got that one from. Now, the last one I want to look at is the one that's mentioned up here, which is the dissociation constant of an acid. Now, first of all, is there a general formula for an acid? We've got HCl, H2SO4, H2CO3, HNO3. They're the ones we're used to. But what's the general formula? When we're dealing with acids in a general form, we use the following symbol, Ha. Okay, that represents an acid. If you notice with all the acids I just mentioned a moment ago, they all begin with H. So therefore, if this is a good strong acid, what's it going to do? It's going to set up a dynamic equilibrium with its own ions post-dissociation, H plus and A minus. So therefore, your Ka comes out to be H plus times A concentration of A minus over the concentration of the original acid, which was Ha. And again, we notice that it's kind of similar to the one that's up here. Ha will dissociate into the equal numbers of H plus and OH, and A minus in this case here, to give me a shorthand form for this. Now, Kc, equilibrium constant expression. Kw, dissociation constant of water. Ka, dissociation constant of an acid. Where do they come from? They come from their associated dynamic equilibrium expressions. Okay, to what's going on in their systems when A and B react to give C, or when water breaks up into its ions, or when an acid breaks up into its ions. So what I want you to remember is this. Ka, as you can see from here now, is called the dissociation constant. Okay, and here's the key thing. The larger the value of Ka, the more towards the right-hand side we go. Remember what I told you that in terms of concentration? The larger the value of Kc, the more towards completion the reaction went. Same theory. The bigger the value of Ka, the more towards completion it goes. Which means that if you have a Ka value that is large, you have an acid that breaks up very well in solution, i.e. a strong acid. If your Ka value is tiny, well then you've got an acid that's not doing too well in water, not breaking up, not dissociating very well, which means you have a weak acid. So Ka, if it's large, represents a strong acid, and if it's tiny, represents a weak acid, because again, it's telling you something about how far the reaction goes towards producing ions in solution. Okay. So, the strength of an acid depends on its power of dissociation. So you take Ha, which is a general formula for an acid. It sets up a dynamic equilibrium with its own ions in solution. Now you could apply the normal equilibrium constant expression to get the following. that Ka is equal to the concentration of H plus to be squared over HA, and I told you already why. They are produced in equal numbers. Okay, H plus and A minus, 1:1. So therefore they're the same number. So when you multiply a number by itself, you get squared. All right. And Ka is a unique value for every single acid. So every acid has its own Ka. If it's high, it's a strong acid. If it's low, it's a weak acid. Strong acids have large Ka because they dissociate well. Strong acids have weak conjugate bases. Now, what does that mean? Think about that for a moment. If I have HA setting up a dynamic equilibrium with H plus and A minus, if I have a strong acid, that means that the equilibrium is going to be over here. In other words, it's going to favour the production of ions. Now, if you're operating over here, that means you favour the right-hand side. You favour dissociation, which means that the reaction doesn't really want to go back. It doesn't want to go back towards the original acid itself. It prefers to be dissociated. So that means if the forward reaction is good and strong, the backward reaction is going to be very, very slow or weak. And going backwards, we talk about conjugate base of an acid. So if you're going forward, the acid and the conjugate base, there's the acid and there's the conjugate base, which means that the conjugate base is going to be very weak because it doesn't want to go backwards. Okay? Now, what about weak acids? Well, weak acids have a small Ka value, and that means that they don't dissociate well. In fact, they prefer to stay together. And if you prefer to stay together, well, that means that your equilibrium is going to be on the left-hand side, favouring staying as you are, not breaking up. And if you're favouring staying with the reactants, then that means you're going to have a very, very strong conjugate base because it'll always want to go back. So I suppose you could write it like this: HA, H plus, and A minus. Okay. If this is a strong acid, equilibrium will favour the forward reaction over the backward one. See that? See the way the symbol changes? Which means that it'll prefer to stay over here, giving you a strong acid, but a very, very weak conjugate base. Now, in this case, you have HA giving you H plus and A minus. But if it's a weak acid, what does that mean? Equilibrium is going to prefer to stay over here, and it ain't going to go very, very far at all over this way. So what does that mean? You've got a very, very weak acid and a very, very strong conjugate base. Because if the conjugate base is formed at all, it runs straight back to give me the original acid. Here, if the conjugate base is formed, it wants to stay that way. And the conjugate base doesn't want to react, making it extremely weak. So here's a question that came up one year in the exams, just taking all that into consideration, and I suppose taking a pause to just go over some of the stuff we've already done. The typical question that comes up before: define an acid and a conjugate pair in terms of Bronsted-Lowry theory. Now, you know this from your previous chapter. An acid in Bronsted-Lowry theory is a proton donor. A conjugate pair is any pair of species that differ from one another by a single proton. We know that. Sulfuric acid associates in water as follows: H2SO4 plus H2O sets up dynamic equilibrium with H3O plus and HSO4 minus. Why is H2SO4 considered to be a strong acid? Now, the answer for that is because H2SO4 produces a huge amount of H3O plus in solution. Or to put it another way, because we've already been speaking about Bronsted-Lowry, you could say, why is H2SO4 considered to be a strong acid? Because it's an excellent proton donor. Okay, it's an excellent proton donor. And why is the conjugate base of H2SO4 described as being a weak base? Now, same thing again. If you have this acid dissociating extremely well, you're going to have a large arrow this way and a little small arrow going this way. So therefore, the overall thrust of this is to stay on the right-hand side. And if you want to stay on the right-hand side, that means that this conjugate base here will not go back towards the original acid. And if the conjugate base won't move backwards, then it's a weak conjugate base. Okay. Show by means of an equation that conjugate base of H2SO4 can itself act as an acid. Now, what is the conjugate base? The conjugate base is HSO4 minus. If it's acting as an acid, what is it doing? Well, it's producing H plus ions in solution, which means that again it'll set up a dynamic equilibrium with its own ions. So there's the equation, that HSO4, if it's acting as an acid, it means it produces H plus, or it's a good proton donor, and obviously then the only thing that's left when you take the remaining H off, SO4 2 minus. So I want to take a journey back to this calculating the pH of acids for a moment, because we already know that when you calculate the pH of an acid, the pH of an acid is equal to minus the log of the hydrogen ion concentration. You worked on that in your previous set of slides. Okay, so therefore, if we were given the pH and we wanted to work out the hydrogen ion concentration, we just stick the pH above the base 10 and that will give me back the hydrogen ion concentration. We've worked on that. That was your previous exercise. Solutions of acids have a pH which depends totally on the hydrogen ion concentration. Therefore, we must always calculate the H plus concentration before we apply the pH formula. You now know that. Okay, if I give you a certain molarity or a certain concentration of H plus ions in solution, you simply stick them into the formula. But you don't use the formula unless you know the concentration of H plus. Now, what happens if they don't give you the concentration of H plus? What happens if they give something like this? Calculate the pH of a 0.4 molar solution of H2SO4. Now, what do I know? First of all, calculate the pH. Write it down. pH equals minus the log of the hydrogen ion concentration. Now, the question is, what is the hydrogen ion concentration? I only know what the concentration of the acid is. So here's what I want you to think of. It's a 0.4 molar solution of H2SO4. That means that you're producing, or you have 0.4 moles in a litre of solution. Now, think of the acid. For every 1 molecule of H2SO4, how many hydrogens can it give out? And the answer is it can give out 2. So therefore, because it can give out 2 H+, the ratio between the molecule and the number of hydrogen ions it produces is 1:2. So if the molarity of the acid is 0.4 molar, then the molarity of H+ would be twice that, 0.8 molar, which means now I can call in minus the pH equals minus the log of the hydrogen ion concentration and put down my 0.8 molar, because that is the concentration of hydrogen ions. And you go to your trusty calculator and you type in minus the log and you put in 0.8 and you close your bracket and you end up getting 0.097 as your pH. Okay, so a very, very low pH, but that's how it's done. So if they give you the concentration of the acid, you have to ask yourself a question. Is the acid monoprotic? In other words, does it produce 1 proton? Is it diprotic, as in the case here, or is it triprotic? And based on the number of hydrogens that it can give, there will be a ratio between the original molecule and the number of H pluses that it produces as a result of dissociation. Now again, I have that stuff already typed there for you, so you can go through it yourself. The solution contains 0.4 molars of H2SO4 per litre. H2SO4 is diprotic because it contains 2 H's, you know. So therefore, there will be twice the amount of H+, which is 0.8 moles per litre, and you shove it into the equation to get your 0.097. Okay, next one. Calculate the pH of a solution that contains 5 grams of HCl in 200 centimeters cubed of solution. Now, we've got 2 things to worry about here. First of all, pH. pH equals minus the log of the hydrogen ion concentration, meaning that your hydrogen ion concentration must be in moles per litre. What have I got here? Grams per 200. I have to go to moles per litre. So I've got 2 things to work on. First of all, I've got to bring 200 centimeters cubed to a litre, and secondly, I've got to bring the number of grams up to moles. Let's do that step by step. Let's do the first thing. Let's bring the 200 up to the litre by multiplying by 5. That's my 1 litre. Do the same over here. That's 25 grams. So I now have 25 grams of HCl in 1 litre. But I want to go to moles. And the way to go to moles is to divide 25 by the mass of HCl. So take out your 25, divide it by the mass of HCl, which is 36.5. And that will tell you very quickly 25 divided by 36.5. And that comes out as 0.685. Not 0.685 moles per litre. So I now have 0.685 moles per litre of the HCl. So I've turned my 5 grams in 200 into grams per litre first of all, which is 25 grams per litre, and then into moles per litre by taking my 25, dividing by the mass of the molecule to get my 0.685. But I'm not finished. Now, 0.685 moles per litre of HCl. Look at HCl. Is it monoprotic, diprotic, or triprotic? And the answer is mono. So therefore, for one molecule of the acid, you will simply get 1 H+. So there's a 1-to-1 relationship between the acid and the number of hydrogens it produces in dissociation. So 0.685 molar and the number of H must be exactly the same. So finally, you then take your 0.685 molar solution of H pluses into the formula pH equals minus the log of 0.685. And again, ask your calculator, minus the log of 0.685, close the brackets, and that comes out as 0.164. 0.164 in terms of your pH. And that's it. So again, see the way the stoichiometry is coming back in? pH, you have to have moles per litre of the H+. If you don't have moles per litre of the H+, you go and find it. You go and do it. Okay. And again, this question here is printed out for you. Moles per litre. So 5 grams in 200 is 25 in 1,000. Turn the grams into moles. So 25 divided by 36.5 gives you the moles per litre. HCl is monoprotic, which means it's a 1-to-1 relationship between the hydrogens and the molecule of the original acid, giving you 0.68 moles of H+, which is then fed into the pH formula to give you your pH of 0.17. Okay, let's take these. Calculate the pH of a solution containing 0.075 grams of HNO3 per 200 centimeters cubed of solution. Now, when I see pH, calculate the pH, I write down the formula immediately, which reminds me that I cannot use this formula unless I have the hydrogen ion concentration. So down here, I notice that I've got grams per 200. Concentration is moles per litre. So I've got a job to do on that number, and I've got a job to do here. Let's do the easy one. Let's bring this up to 1 litre by multiplying by 5. So we're going to do the same thing here. Multiply that by 5, and let's see how many grams I have in a litre. So 0.075 times 5 comes out as 0.375. So I've got 0.375 grams in 1 litre. But grams per litre are no good. I've got to turn my grams into moles, which means I take my HNO3, which is 1 plus 14 plus 48, that's 63. So 0.375 divided by 63 comes out as 0.00595 moles per litre of HNO3. That's the acid. Okay. Now, how many hydrogens does it contain? It only contains 1. So straight away, it'll also be 0.00595 of H+, which I now feed into my formula to get my pH as minus the log of 0.00595, and go back to your calculator, minus log 0.00595, and that comes out as 2.23. And that's your pH. Okay, last one. Calculate the pH of a solution containing 24 grams of H2SO4 per 1.25 litres. Now again, calculate the pH. Let me just take out the ink on top of that. Calculate the pH of a solution. Again, when you hear calculate the pH, you write down the formula. Okay, which means hydrogen ions must be in moles per litre. Okay, so now I've got to remember moles per litre. What have they given me? Grams per 1.25. So the first thing I'm going to do is bring this to 1 litre. And the quickest way to bring any number to 1 is to divide it by itself. So I'm going to do the same thing over here. Let's divide this by 1.25. So 24 divided by 1.25 comes out as 19.2. So there's 19.2 grams of H2SO4 in 1 litre. Okay, but I don't want grams per litre. I need moles per litre. So you're now going to divide 19.2 by the mass of H2SO4, which is 2 plus 32 plus 64, which is 98. So 19.2 divided by 98 comes out as 0.196. 0.196 moles per litre. Okay, and that's just of the acid. Now, of H2SO4. Okay, how many hydrogens in H2SO4? 2. So therefore, it'll be twice that of H+. So you multiply that by 2, and that's going to give me 0.392 moles per litre of H+, which I now feed into the minus log formula. 0.392, that's my pH, is equal to, and that comes out as minus the log, and that comes out as 0.407. And that's my pH. So again, grams per volume should be turned into grams per litre, then moles per litre. Then check and see, is the acid monoprotic, diprotic or triprotic? And if you need to adjust the number of moles per litre from the acid up to the number of moles per litre of H+, do so before you fill it in to the minus log formula. Okay, so I'm going to ask you to pause. I'm going to ask you to try these questions here. They're quite straightforward, but please remember that check and see, are they mono, di or triprotic acids? Adjust the concentration of H+ before you shove it into the formula, because usually the concentration of the acid and the concentration of the H+ are in a ratio of whatever number of H+ are in the molecule to one molecule. Okay. Just one final look at this. Let's calculate the pH of bases. Now, look, it's exactly the same thing. Everything we've learned up to now has exactly the same formula, except now we're dealing with pH, the pH of a base, pH up above 7. Acids produce H+, bases produce OH-. So to calculate the pH of a base, we must first calculate its pOH. Now you'll notice there's a formula. The pOH is equal to minus log of the OH- ion concentration. Same formula. So when you're dealing with bases, the first thing we do is we apply the formula as normal. But then we've got to remember that we're working on the other side of the scale. We're working on the side of the scale that's above 7. So to turn a pOH into a pH, we take use of this formula here. The pH of any base is 14 minus its pOH. You will never be asked for the pOH. You'll never be asked for a value up at the other end of the scale. You're always asked for pH. So you work out the pOH as normal, and then you take it away from 14. So again, let's take a couple of examples. Calculate the pH of a solution containing 9 grams of sodium hydroxide in 500 centimeters of water. Okay, first of all, calculate the pH of a base. Do you notice that? You can't directly get the pH of a base. So the first thing we do is we remember that the pH is equal to 14 minus the pOH. And then we say that the pOH is minus the log of the OH- ion concentration. Now, OH-, that means that I want moles per litre. What have I got? Grams per half litre. So the first thing I do is multiply that by 2 and multiply that by 2 to get it into grams per litre. And that will be 18 grams. And then I turn this into moles by dividing it by the mass of sodium hydroxide, which is 23, 24 and 16, which is 40. Okay. So the number of moles of NaOH is 18 divided by 40, which comes out as 0.45. Okay. AOH in 1 litre. Now, think, how many OHs does sodium hydroxide make? And the answer is 1. So 1 molecule of NaOH makes 1 OH. 1:1. So therefore, that will also be 0.45 moles of OH minus. So what do? I put that into the pOH formula. Okay, so therefore pOH equals minus the log of the OH minus ion concentration, which is minus the log of what? Well, 0.45. And if you go to your calculator, minus the log of 0.45 equals 0.347. But that's the pOH. Finally, to get the pH, it's 14 minus 0.347, and that comes out as 14 minus that, which is 13.653, and that is the pH. So what are the steps behind it? Number 1, turn the grams per volume into moles per litre. Okay, work out what's the concentration of OH minuses in that solution. Put the OH minus ion concentration into the pOH formula and work out the pOH by getting minus the log of the OH minus ion concentration. Then take that value away from 14 to turn it into the pH. So there's only one little step extra, and that is to get the pOH away from 14 to get the pH. Okay, next one. Well, we've done that's the one I worked on already. So that's the solution, as we said. You can take a look at that yourselves. You can pause it now if you want to take a look at that. And then you've got your 14 minus your 0.49, which is 13.51. Okay, that's the solution of the previous question. Okay, now I'm going to take 2 of these, and then I'm going to leave you with the rest of these plus these to do yourselves. Okay, so let me take 1 of each. I'll take I'll take this one here, and I'll take, oh sure, why not, let's just take that one. So B and E. So let's take part B first of all. We've got a 5 molar NaOH, and they want me to calculate the pH. Now, pH equals minus the log of the hydrogen ion concentration. Problem, we're not dealing with acids, we're dealing with bases. So you immediately write down the following. pOH equals minus the log of the OH minus ion concentration. Can I find that? Yes, I can. We've got a 5 molar NaOH solution. Now, how many OHs does 1 molecule of NaOH make? And the answer is 1. So therefore it's 1:1. So if the molarity of the base is 5 molar, then the molarity of OH will also be 5 molar. So the OH concentration equals 5 molar. That goes in here as the pOH equals minus the log of 5. And minus the log of 5 comes out as minus 0.699, or if you want to, because it's so close, minus 0.7. Okay, so now what do? Now I've got to remember that pH equals 14 minus pOH. So that's going to be 14 minus, which we had up here, minus 0.7. And when you add those together, you get 14.7 as your pH. Remember I told you there are pH values above 14. So don't be surprised if you calculate a pH value that's greater than 14 or less than 0. It does happen. Okay, so that's the first one. Second one, 0.37 grams of CaOH2. Okay, I want to get the pH of that. pH equals minus the log of the hydrogen ion concentration. What? Can't use it. pOH is minus the log of the OH minus ion concentration, and I can use that. So I go back over here, because it is OH, I go back over, and I want OH minus in moles per litre. So I don't have it. What have I got? I've got 0.37 grams of that in 500 centimeters cubed. Okay. So now the first thing I've got to do is get that up to 1 litre by multiplying it by 2. So let's multiply this side by 2 as well and see how many grams we have in a litre. So 0.37 multiplied by 2 comes out as 0.74 in 1 litre. And finally, to get this into moles per litre, I divide by the mass of the molecule. Calcium, if I remember correctly, is 40. Plus 2 oxygens, that's 32, and 2 hydrogens is 2, and that brings me up to 74. So 0.74 divided by 74, 0.1 molar CaOH2. That's the molarity of the base. Now, how many OHs are present in one molecule? One molecule gives 2 OHs. So that means that 0.1 molar base will give 0.2 molar OH minus ions, which I now bring up here and get the pOH first of all. So it's minus the log of 0.2. And minus the log of 0.2 comes out as 0.699. So again, we get 0.7. Just leave it as 0.7, round it off. And the pH will be 14 minus 0.7, which is 13.3. And that's your pH of that one. So I've done already, I've looked at this part B. So I've looked at part B and I've looked at part E. So I want you to take A, C, D from this one here. So you can pause that now and work on A, C, and D. And when you've got this finished, you then may move on to the next page, which involves these questions. So pause them, get them done, have a look at them. We'll come back and take a look at the OHs in particular at the start of the next class before we go on to finish this thing. And to finish the chapter, we're going to look at weak acids and weak bases and their corresponding levels of dissociation.